to other traffic participants, so that will then also lead to an improved safety to this. In this study, what I'm now today presenting, we made a kind of, I have to say, 3 case studies where we discussing these kind of applications, of course, with the intention, do we have the correct light sources for this? So we talk about, of course, different performance criteria of this application to understand, do our current and also future light sources fit to these requirements. And the first of all, if we talk about road projection, then it's of course the visibility, and we have also seen yesterday, it's a very, very crucial criteria. We have seen various criteria that comes to it. So on one hand, the brightness, the overall brightness, but also on the next steps, the homogeneity and sharpness of these kind of projections is very important. Then from our point of view, from light source manufacturers, it's of course very important that we learn how many of these photons Mr. Norman has shown are needed, because okay, it's a combination of brightness and efficiency of the system that is then basically defining how much flux is required. And then of course we have also learned that different colors and also the dynamic of these kind of projection is very important to, let's say, make it visible for the other road users. Let's start first with brightness and let's say the basic, conditions. Like I said, what we looking in our case studies, these different applications, these are all kind of applications that are more or less critical to be seen. Maybe they are safety related, directly or indirectly, and that's the question under what kind of conditions they need to be seen. And of course, if you have the wish that it's always be seen, let's say under bright daylight, then you would asking for something like illumination levels of 10,000 lux. But then very quickly you can derive if you want to have something like a square meter projection, so that it's a reasonable size, and on the other hand you want to have 10,000 lux on the ground, that you easily end up with requirements in the beam of already 10,000 lumen. And that's much more than, let's say, what is even for headlighting would be required. So let's say we have to stay a little bit more reasonable, but of course I was looking for applications that coming not on this level, but coming closer to these kind of levels. So let's say maybe we have to restrict to more dusk and dawn, or overcast sky conditions, or in a parking garage, of course, it's less bright, and then we more talking about the range of 1,000 lux. That would be, of course, thing. And I would not like to discuss today, let's say, the legal situation. Again, this study is, okay, how far can we get with existing, or let's say, next level high luminance sources, but not, let's say, with very fancy laser scanning things. Okay. Coming to the applications. The study I would like to cover different application use cases. So let's say first of all we started with the extension of the turn signal on the ground, and here we selected also different an optical system where we said, okay, let's be as efficient as possible and make it also compact. So let's say you don't want to have a lot of real estate at the car, should fit in various positions. And let's say make a very efficient and compact design. Then we looked at a backup scenario where, let's say, some warning lines will be projected that let's say can show that the car is backupping and indicated, and then also be enhancing, let's say, okay, when we would like to add dynamics, how would it look like? So of course we have to make also the optical system some compromises. Still, the efficiency should be rather high. And then we looked a little bit more high-end in systems where we have a really sharp, very homogeneous pattern, where we can have dynamic, and there we selected a microlens array based system, where we illuminated the microlens with, let's say, 9 different sections. I will come to this. Again, this study is not intended to, let's say, creating final designed modules. No? So it's more, okay, we making these mock-ups and we design them, but let's say in the sense it is, we want to use more or less state-of-the-art technology, nothing very special for this. And the light sources are high brightness colored or white light sources, but also not very, let's say these are more or less qualified light sources on the market. Okay, coming to the first system, so we can see we designed a gobo-like system, what is very heterodyne conserving, so let's say optimized of what we can achieve. If you're looking at the cross-section here, you can see we have placed the LED behind a pre-collimation, we have a first optic combined, and this is here fitting the emission angle through the final optic, and in between we have a gobo, an aperture, what is then basically the symbol what we're projecting. With this system we can be rather efficient, we're getting more than 30% of the photons created on the road. Let's say if we start with 250 lumen, that's an amber LED for this turn signal, then let's say we can realize something like 3000 candela and 78 lumen on the ground. Of course, that is mainly related that still some light is of course blocked by the gobo. It would be maybe a different efficiency if there would a different design of the aperture. And still then with these we can make, let's say, in 1.5 meter distance, something like 1,000, between 500 and 1,000 lux on the ground. So it should be not visible at bright daylight, but let's say we can see it on the booth, for example, with these kind of illumination condition very well. The second system, then we said, okay, we want to combine also some kind of dynamics into the system. Let's look a little bit more detailed into what we have here. We have combined always 2 LEDs to get more flux into each channel. We have 3 stripes that can be switched on individually. And we realize this by, okay, have 3 different pre-optic channels. Again, we focusing with these pre-optics through the gobo, through the aperture, on the and then onto this lens to be rather efficient. It's not the same kind of efficiency, but it is still well above 20%, something a little less than 30% efficiency. Then we have installed something like 1,400 lumen, 1,000 lumen white, 400 lumen amber. We could have a little bit more amber from the LEDs, but I say for reasonable power consumption, something like this. And then again, we reaching illumination levels, let's say between 100 and 150 and 800 lumen on the ground and 1.50 meter distance. The field of view is for sure bigger. Okay, it should be well visible from behind of the car. And again, now we have used here, more or less state-of-the-art LEDs. Of course, high brightness, but not really high luminance LEDs. And then we go to, if we go to the third system, then we have combined a micro lens array. The system is much more compact. It's a very small, very compact system. Now we use the 3x3 LED array. So in this case, we used high luminance LEDs with a very small light emitting area. And all these LEDs are, let's say, have an individual pre-optic channel. So we have 9 channels, and these are projecting light to 9 different sections on the micro lens array. And in the micro lens arrays, we have 3 different kind of apertures. For each stripe, 1 aperture. So let's say 3 stripes, 3 kind of apertures, then that's selectively illuminated. With these we have a really flat, narrow system, and but the overall efficiency, now we're installing, in case we install something like 2000 lumen, and still get only something like 80 lumen on the ground. The efficiency is in the range of 5%. That is mainly related to the aperture we use, because 3 stripes means that we have basically always something like 20% transmission of the aperture, simply because all the rest is blocked. So there's a little principal problem. If you would have a different kind of image, then of course the efficiency would be higher. However, these kind of small light sources are fitting very well to the opening angle of the micro LED channels. We need to collimate something like the range of 12 degrees, between 11 and 12 degrees, to get a crosstalk free projection out of these micro lens array. To even enhance the luminance, let's say for the different stripes, and let's say modify the total brightness of the different stripes, we now have the freedom, because we have only 3 stripes. Theoretically we could have 9 different images. Now we have only 3 different positions to make. Let's say the center LED is going to with the center light lens going to the center part, and we have then here the chrome mask for the first stripe. In the case for the second stripe, we have now combined 2 LEDs. We have 2 channels, and these 2 channels are generating here with the second type of chrome mask, then the second image, and then for the last image, to get it brighter, naturally it would be of course going dim, but let's say the further out part should be the brightest. We combine 6 LEDs, so 6 channels together to make these stripes appear as the brightest. Now coming to the light source, because it's basically, okay, what is required for the light source? If you're looking at, let's say, for all the system as a kind of what is common, we have seen, okay, we need the light sources have a certain luminance, at least something like 100 meganits or even more would be beneficial. In the case of the high luminance light source, we could go even to 200 meganits. But then, of course, the efficiency of this light source goes down, and the overall power consumption of the system becomes immense. No? So let's say that is maybe too much. So let's say we need the light sources that at least by still in a reasonable efficiency level in combination with high luminance. So this kind of combination is required. And of course for PCM where everything is a little bit less because we have these amber photons, but still also here reasonable luminance is very important. To minimize the size of the optic and still get a large flux on the road. Then we see we need really a various range on flux package. We started from 250 lumen from the source to get a small static projection and ended up with something like 2000. We could have even get 3000 lumen out of this system to, let's say, get bigger projections that are nicely visible. And that means that we need to combine light sources. It's maybe not one unique light source, and that we need a kind of combination. And that is, I think, possible because, let's say, still we have, for example, the ability to put in LEDs close to each other. In this case, of course, we need at least the ability that we have a kind of short edge at the top, so that we're getting one compact light source if we're combining different light sources, or we do it in this way, that we then combine the light source later in the projection plane. Both is possible, and that by this flexibility we can either get, let's say, efficient small projections, or if you want to have really large projections, then we apply more flux on the ground. And then we also have the need of course, different colors. The study was based on, let's say, amber and white, but of course we can also discuss to use PC red to make, let's say, high brightness red LEDs in case this is really required. And of course that is maybe pending for regulation before we consider this further, and the same would be the case for the cyan case, where we maybe indicate some autonomous activities. This brings me to the conclusion. So basically, now what we have seen is that to get a high efficient system, we also need high efficient and let's say high luminance sources with a lot of power and flux, and still a compact source kind of source. We need, we have of course also shown different possibilities to create dynamics within one module. Of course, we have seen modules, let's say, you can always combine different modules, but also within one module we can create a kind of dynamic by switching the individual sources. or using different colors that can be switched on. What is very important learning when he's looking at the case, for example, for the microlens array and is compared to the gobo, the dynamic illuminated gobo, we have to look that the optical system is matching to the kind of application what we like to project on the road. So depending on what we want to project, maybe different optical systems are beneficial. Of course, there are more requirements to have, of course, also, let's say, overall compactness. If this is leading, then maybe that can also influence the choice for the system. And then last but not least, I'm afraid that finally to get all what we can maybe think and dream about, that this can be in the end also be limited by the available power consumption or cooling ability, because if you later, and you can see it at the booth, we have all these demonstrators there, the size of the modules is often dominated more by the thermal management and not by the optical system. So let's say this needs to be maybe also be considered. So with this, yeah, I welcome you at our booth and thank you.